All right, welcome to this video. And in this video, I'm actually going to do problem 2 on the final exam with you. And then I want you to follow along and do what I do on paper and in Microsoft Excel. Okay. So what we're going to do is we have this ventilation system. And what we're going to do is we're going to create an equation and plot basically the operating point. Okay, so you're going to end up creating this. All right. I'm going to step by step and show you and how I would want it done. Okay. So let's read the problem and then I'll start it. So a local ventilation system, a hood and a duct system, is used to remove air contaminants from a pharmaceutical lab, which is the figure on the left. The inner diameter of the duct is D equals 150 millimeters. Its average roughness is 0.15 millimeters, and its total length is L equals 24.5 meters. There are 3 elbows along the duct, each with a minor loss of 0.21. Literature from the hood manufacturer lists the hood entry loss coefficient as 3.3 based on duct velocity. When the damper is fully open, its loss coefficient is 1.8. The minor loss coefficient through the 90-degree T is 0.36. Finally, a one-way valve is installed to prevent contaminants from a second hood from flowing backwards into the room. The minor loss coefficient of the open one-way valve is 6.6. The performance data of the fan fit a parabolic curve of the form H available equals H naught minus A V dot squared, where the shutoff head H naught equals 60.0 millimeters of water column. Coefficient A equals 2.5 times 10 to the minus 7 millimeters of water column per liters per minute squared. Available head, H available, is in units of millimeters of water column, and capacity V dot is in units of liters per minute of air. Estimate the volumetric flow rate in liters per minute through the ventilation system. And then for the duct system shown left, plot the required fan head H required, millimeter water column as a function of volume flow rate, V dot, liters per minute. On the same plot, compare a variable fan head H available versus V dot and mark the operating point and discuss. Whew, that's a lot. This is a very good problem. And hopefully when we start it, you have an idea of where to start already. And by the time I'm done, you'll understand how to do these particular problems. So I'm going to zoom in here. So point 1 is down here. That comes in, goes to the damper, through the fan, through these elbows, through this one-way valve, through this T, and then back out. We have a datum. Z1 is down here. Z2 is up here. We have loss coefficients. We have temperature, pressure, and we can go from there. So let's start any particular problem with givens. Given. All right. We have D equals 150 millimeters. E, 0.15 millimeters. L, 24.5 meters. Z1, 0 meters. Z2, 20 meters. Let's fill up here. H naught was 60 millimeters. A is 2.5 e to the minus 7 millimeters per liter per minute squared. And one thing just to kind of teach you now is they're giving you these values, H naught and A, in like water column, but we're using air. So we have to kind of do a conversion to get the right values. So we're going to take the 60 millimeters. We're going to convert that to meters, which is 1 meter over 1,000 millimeters. Then we're going to multiply that by a ratio of density of water to the density of air. Okay, and that's the correct H value. And we'll do this probably in Excel. Okay, we have A now, we have to convert 2.5 e to the minus 7 millimeters per liter per minute squared. 1 meter, there's 1,000 millimeters. And we're going to again multiply that by this ratio of densities to get it to the correct value, because it was given in water column and we're using air, so we need to make sure we convert it. Let's do properties. We have G is 9.81 meters per second squared. Density of water we'll use as 998. You could use 1,000, it doesn't matter. Kilograms per meter cubed. Density of the air is 1 atmosphere, so 101,325 pascals. Temperature of the air, I believe it was 25 degrees C. We'll add 273, which goes to 298 Kelvin. R for air is 287 joules per kilogram K. Mu, dynamic viscosity of air, is 1.895 e to the minus 5 kilograms per meter second. And then the density of air, I'm okay right now. Use ideal gas, P over RT, 101,325 Pascal, divided by 287 joules per kilogram K times what? Temperature is 298 Kelvin. We get 1.18 kilograms per meter cubed. All right, and I'm going to keep scrolling over. We're going to find the operating point, OP, and sketch. We'll just say C diagram. You can just copy it or just put that. I'm okay with that. And just like a side note, I'm going to put K losses, so we have those in a section. We have a one-way at 6.6. We have 3 elbows at 0.21. We have an entry loss at 3.3. We have a damper at 1.8. We have a 90-degree elbow at 0.36. And the K total comes out to be 15.93. Okay. And I believe I ended up, how did I do that? Yeah, I just put the total value in there, I believe. I think I added them up. Yep. You'll see. All right. Now let's get to the solution. And we're going to write modified Bernoulli's. I'm going to go from 1 to 2. And let's write this famous equation again. P1 over rho G plus V1 squared over 2G plus Z1 plus HP minus HT minus HL equals P2 over rho G plus V2 squared over 2G plus Z2. Now, let's cancel. This is atmospheric. Assume the velocity at 1 is 0 compared to 2. Datum is at 0.1. There's no turbine, and it shoots out to atmospheric. Isn't this lovely when this happens? So HP minus HL equals V2 squared over 2G plus Z2. HP, which is the H required, is going to be V2 squared over 2G plus Z2 plus HL, where HL is V squared over 2G times F L over D plus K total. Okay. So what we just derived is the system HP. This is what we need based on our system. And it gives you the equation where, let's go back up here, for the available value. Okay. So if we plot H V dot, we have this equation is this line. And then the other one we derived is going to be that line, which is basically this. Okay. So what we're going to have to do is we can plot this red line, right? I'll go back to red here. We can plot this one because we have the equation, which is right here. In order to do the blue one, we have the equation, but we need to change our velocity inside, which then really changes your volumetric flow rate. So you can get that on. Well, when we do that, it changes Reynolds number, which then changes your F, because this could be laminar or turbulent, so you have to figure out the right equation to use. Okay? So, this is what I would want on your piece of paper or your handwritten notes. And then what you can just say is see Excel. So let's go through Microsoft Excel and how I would want you to now do the problem in there. Okay. Just move my keyboard. All right. We're doing good. Okay. Let me get this right here now. And let's do File, Save As. And I'm going to save this just right now on my downloads. And I will call it Final Problem 2, ENGS 314, and your last name. Okay? All right. Always, and you've done these before, the top of your page should have this heading. Let me push this up. There we go. Okay. Name, email, your date. So today's the 17th. The class, the homework number or the exam number, problem number, and your description. Okay. Now, I would say the next section is going to be your givens. All right. And I'm going to have, I basically merged this and centered that. But we're going to put our givens. So D, row of W, row of air. Oh, no, sorry. Let's do mu. Your E value, L, G, your K total, Z1, Z2, R, your temperature, your pressure, your row of the air, and what we're going to do is center all of these and put borders on. Okay. Oh, I don't think the borders, I did outside. I want all borders. There we go. Okay, so from the problem, this was 0.15. Did I put the units? Why don't we do this? Put nomenclature and put units here. Okay. This, I believe, was meters. Roll of the water, 998 kilograms per meter cubed. Mu, you can use 1.9, e to the minus 5. And the unit on that, kilogram per meter times second. E, 0.00015. This is in meters. I converted it. Length 24.5. Is that right? Yep. That was unit of meters. And this was lowercase g, which is acceleration due to gravity, 9.81 meters per second squared. K total calculated to be 15.93. Z1, 0 meters. Z2 is 20 meters. R is 287. This is joules per kilogram K. Temperature, 298 Kelvin. This is 101,325 Pascal. And this would calculate it to be 1.18. But let me show you something. We can put an equation in here. So equals, it's going to be what? Pressure divided by parenthesis R times T. So you can put those cell numbers in and calculate it. And you see how this gets a long number. You can go up here and you can increase the decimal or you can decrease the decimal. And let's just do to the hundreds. Okay. And I'm going to copy paste this unit. Now, I'm not going to finish the nomenclature, but I would like you to. This is diameter. This would be density of water, dynamic viscosity of air, viscosity of air, and so forth. Okay. This would be your roughness. Just to save some time, I do want you to finish this, but we still have a lot to go in this problem. Okay. All right. Next section is, I'm going to put it right here, pump information for the curve. So I'm going to type that in. I'm going to highlight these three cells. I'm going to merge and center and put a border on. And then I have 1, 2, 3, 4, 5. Okay, I'll just go right here. So what we have is H naught. We have A. And then I'll get into the solution. And then you have area. So let me just center all of these. We got borders on. This was going to be 60, right? Times, oh no, we'll do open parentheses, 60 divided by 1,000 for conversion, times open parenthesis, density of water, which is this cell, divided by, which that cell was B13, the density of air, which is B24. Close parenthesis, hit enter. And let's change this to that. Same with A, you put equals. You're going to click or type 2.5 e to the negative 7. We do need to put an open parenthesis before the 2, so we'll put that there. And we're going to divide by 1,000, so close parenthesis, times open parenthesis, density of water, which is B13, divided by B24, which is the density of air. And let's go ahead and do 2.11. Is that what I got? You in mind? Yep, perfect. Okay. And you can put the units and the nomenclature in. Let's continue these down for center and borders. Okay. So units, nomenclature, keep putting those down. All right. Solution. Highlight this, merge and center. Let's make these bold. So I clicked on the given cells. Let's make it bold, and let's make this bold and underlined. Okay. So we have basically the heading at the top. We have our givens. We have our pump information. We can now start the solution. Is this underlined? No. Let's underline it and make it bold. The area is just going to be equals, and it's pi open close parenthesis times d divided by 2, and we got to put these in parentheses. So open parenthesis before the b and close parenthesis after the 2 and do square root or caret, which is shift 6, 2. And let's make this to the nearest thousandths for that. All right, we're getting there. We're getting there. Whew. All right, 20 minutes in. Let's save it. And now what we're going to do is we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9 columns where we're going to have velocity, flow rate, conversion for flow rate, H available, Reynolds number. It's going to tell us, is it laminar or turbulent, the F value, HL, and H required. And the cool thing is we only have to do we have to do like one equation and then we can extrapolate down. So let's go V meters per second, V dot meters cubed per second, V dot, this would be liters per minute, LPM, and then we have H available, we have Reynolds number, we have laminar or turbulent, we have, I'm going to make this cell bigger, F, HL, and H required. I didn't put units on here, so let's put units. Reynolds number is unitless, that's unitless, that's unitless, meters, and H required is meters. All right, so right now I'm just going to make sure everything is centered and with borders for this. All right, okay. So what we're going to do is, what did I end up doing? I went 0.5, sure, okay. So we're going to start, let's just start with 0 for now, okay? And we're going to go right now, we're going to say in cell A34, put equals, click on cell A33, and hit the plus 0.01 for right now, okay? Then you hit enter, you go back in the cell A34, and you can left click and drag down a few spots. Boom. Okay. Now, we can calculate V dot by saying, so go into cell B33, say equals, and then that's flow rate is velocity times area, right? So you're going to click the velocity cell, which is A33. You're going to do multiplication, and you're going to click on the area, which is cell B30. Now, what we're going to do is we want to, this number of the area stays the same, and we're going to use the same cell throughout these columns. So what you need to do is right before the B, hold shift 4, which is the $sign. So put a $sign there and a $sign there, which keeps that cell all the way down. For example, so if I hit enter, go back into B33, and I left click on the corner here. See how my cursor changed? Left click and I drag down. Each one of these uses that area, okay? Otherwise, if we don't do that, it wouldn't work right, okay? It would actually pick up this value, and so forth. So I'm going to keep those for right now. All right. Now we can convert this. So in cell C33, click equals. Then you're going to click on the V dot meters cubed per second cell, which is B33. You're going to multiply that by 60,000 and hit enter. Then you can click back into this cell C33, left click and drag down on the bottom right corner of that cell and let go. All right, cool. Okay, now H available, that was that equation that was given in the problem. So in cell D33, click equals. And it's going to be, if you remember, this cell H naught B26 minus A, which is B27, times your volumetric flow rate squared, which is in liters per minute. So it's in cell C33. And then that is squared. So shift 6, which is your caret, and then type 2. Now, again, you see how B26 and B27, those are constants. So we need to put dollar signs between the B and before the 2. And same here. Dollar sign before the B, dollar sign after the B. But this volumetric flow rate, that changes, so we're going to keep it. So hit enter, and you can then go to the bottom right corner, left click, and drag down. And let's make these right there for now. You'll see, we can change that in a minute. All right, next column, E33 is Reynolds number, which is, remember, rho V squared, or sorry, rho VD over mu. Okay, so let's go ahead and plug this in. Cell E33, click equals. Then you're going to have open parenthesis, and it's the density of the air, which is cell B24, right, times your velocity, which is A33, okay, times, should be B12, your diameter, okay, close parenthesis, so let me go back down, close parenthesis, divided by mu, which is B14. Click that. Now, you notice that we have values up in our given, so we need to make sure that we put dollar signs there. Dollar sign here before the B, after the B, and then on B12, you need it before the B and after the B. And same for B14, before the B, after the B. Click enter. Click back on the cell E33, find the bottom right corner, change that to these little black small plus, left click and drag down. Okay, we now have Reynolds number, and I'm going to make it a little bit bigger there. Okay, cool. Now we can write what we call an if statement, and I'm going to copy and paste this so you can see it here. Oh, cancel. Actually, I can type it for you. All right. So in cell F33, click equals. Then write if, open parenthesis. Then we're going to click on E33. So left click that. And say less than, which is the less than symbol, 4,000. Put comma. Put quotations, which is shift quotations, which is right next to the enter. Then type in laminar, close the quotation, comma, open quotation, turbulent. Type that. Close your quotation, close parenthesis, and then we'll end up we'll hit enter. So basically, we're writing an if statement to say if that number is less than 4,000 is laminar, or if it's not, it's turbulent. And then click enter. Go back into the cell F33, find the bottom right corner, change your crosshairs, left click and drag down. Okay? And it should be all turbulent for a while. Okay. Now, we know that the F equation is dependent on laminar or turbulent. Okay, so let's do the laminar equation. So go to cell G33, type equals, open parenthesis, if, open parenthesis, and we're going to click on F33. So left click on that cell. Equals sign, quotation, laminar, end quotation, comma, 64 divided by, then you're going to click on cell E33. Okay. So that's saying if it says laminar in cell F33, we're going to use 64 over the Reynolds number. Else, or we're going to use the turbulent equation, which I'm going to give you a simplified one to use, which we can use, because remember we have to use the Moody chart or that implicit equation. It gets tricky. So we can use this one, which it's comma 0.25 divided by, open parenthesis, type log, log, 10, open parenthesis. Then we're going to click on cell B15, which is our roughness. And we're going to put dollar signs on that because that's in our givens. So dollar sign before the B and after the B. All right, and I'm going to go back up. Yeah, you should be able to see where we are here. So we're at B3, and then we're going to say divided by, open parenthesis, 3.7 times B12. And B12 is our diameter, so click that. And that also needs, I'm going to scroll down so you can see, dollar sign before the B, dollar sign after the B. Okay? Now we're going to close. So we wrote 2 close parentheses. Then we're going to write a plus sign, open parenthesis, 5.74 divided by, open parenthesis, E33, which is the Reynolds number, caret 0.9. And then we're going to close, we're going to have 3 closed parentheses. 1, 2, 3. And then we're going to caret 2, because that's squared. Then we're going to have 2 closed parentheses. And they should close everything. Did we miss? What did I miss here? I must have missed a parenthesis. But I think I fixed it. Let me double check to see where I screwed up here. Close. There's an open. Should be 1, 2, 3. 1, 2, 3. And then 1, 2. What did I miss? Oh, we did not need the parenthesis here at the start or the end. Okay, that should work. All right. Now go back into cell G33, find the bottom right corner of that cell, left click and drag down. Okay. Cool. All right. Now let's get to HL, which that was on our paper. Let's go ahead and go to cell H33, write equals. And then we're going to click on, I believe it's A33. Oh, A33. And then we're going to say caret squared, because it's V squared, times 0.5 or divided by 2, it doesn't matter, times, open parenthesis, 1 divided by B17, which is our acceleration due to gravity. We're got to put dollar signs before and after the B. Then we're going to close parenthesis. Then we're going to multiply. We're going to open parenthesis, G33. So we're probably going to have to type it because the equation's in the way. So G33, which is our F, times, open parenthesis, this is going to be L over D. So B16 divided by B12. Now we got to put dollar signs in here. Dollar sign before and after the B. Before and after the B for B12. Then we're going to close parenthesis. Then we're going to add B18, which is our K total. So click on B18 and put dollar signs there because that number's staying the same in all of our equations. And we need to close the parenthesis. Then hit enter. Go back into H33, find the bottom right corner of the cell, left click and drag down. All right, we now have that. We can find H required, which is going to be in cell I33, right, equals. And this is going to be A33. Oh, hold on. Let's type it. I don't know why I did that. A33 caret 2 divided by open parenthesis 2 times G, which is B17, and we need dollar signs there. Before and after the B. Close parenthesis, add H33, which is our HL, right? And then we're going to add Z2, which is B20. And we need dollar signs before and after the B. Click enter. Find cell I33, find the bottom right corner, left click and drag down. All right. Okay, I'm going to zoom out some because I'm going to extrapolate down. What we're going to do is, we're going to go down to, let's go down to 0.5 with this. So if you left click cell A33 and left click and hold all the way to I36, you can find the bottom right corner of all this. It changes to that black crosshair, the small, left click and drag down. And I don't know, go to 100. What do we have? 0.6, okay. What we can do is highlight all of this, left click and drag, and hit delete. Okay, and then what we're going to do is we're just going to change the V to go by 0.5s. All right, just to give you a smaller increment at the start, but then it goes bigger. So we're going to, so basically in cell A84 now, right, equals, click on A83, and then plus 0.5, hit enter, and it should automatically work for you. And now we can highlight that row of 84, find the bottom right corner, left click and drag, and what do we want to go to? What did I end up going to? I went to 10. Okay, so let's go 2 more. 2. Okay. So we didn't have to change anything else because we've pretty much programmed it. You see how it switched from laminar to turbulent for us? All right. We got that transition before we jumped by 0.5s. And we should end up with 125.7. Yep, good. Okay. Now, why don't you highlight row 32, go back to home, make this bold, and let's highlight, left click and drag all the numbers, go all the way down so you can scroll down, and let's make these right to there. Let's do to the nearest thousands is good. Okay, save it, and now we have the data. Now let's make the graph. All right, so I'm going to scroll over here, click on this cell, go to the Insert tab at the top, find the charts. It says Charts. Click on this Insert Scatter Plot, and let's do the scatter with a line. Okay, so this one. So this is called the Scatter with Smooth Lines and Markers. Left click. And I'm going to move this over here. Should be able to move it over there. Yep. So I clicked on the K44. I'm just using my arrow keys to move over. Okay. Now left click on the graph Then you're going to right click. You're going to select data. Over here, click add. So left click. And we're going to do, let's do H required first. The X values. So you're going to click this up arrow, left click this. Then you're going to scroll to the left, and it's going to be volumetric flow rate in liters per minute. Okay, so left click and hold all the way down to 102. Unclick. Then you're going to click this checkbox right here again, left click. And then the Y, click in there and delete. Left click this up arrow, and this was H required. So we're going to left click on from I-33 all the way down to I-102. Let go of your left click. Go back up here, left click this down arrow now. Click OK. Left click OK. And now you should have one graph or one line over here. You're going to right click this graph, select data, click add. Let's call this HAVA. Left click the up arrow. You're going to scroll to the left and find liters per minute. So left click C33, drag down to C102. Let go of your left click. Then go up here where this down arrow is, left click. Click in the series Y, hit backspace and delete those. Left click this up arrow. And we're looking for H available, which is D33. So left click and hold and drag down to D102. Let go of your left click. Go back up here. Left click the down arrow. Click, left click OK. Left click OK. And now you should have hopefully two lines. Uh-oh. What happened? Oh, there we go. I just left clicked and moved and it showed up. But it should show up. If you have issues, let me know. That was weird. I don't know what happened there. So now you have these two lines, okay? And we need to put a title. So if you left click the plus for chart elements, left click axis titles, left click chart titles, and left click legend. So double click in chart title and you can delete this. So hit delete and put H required or available versus flow rate for a ventilation system. Then left click, double click in the axis title for that Y axis, put H with a unit of meter. So brackets or parentheses. I'm going to make this a little bit bigger. So if I'm just left clicking those, double click in this, and this is, I put Q or V dot, and this would be liters per minute. And then you can left click off the graph. And you can left click the title and you should be able to move it by left clicking and dragging. Same with this. Okay. But there you go. You now have solved where the operating point is. And it's pretty much where those two equal each other, right? So right around 50 or 5, maybe 5,200 liters per minute. So we can use that, which we should use, or anything to the left. But we can't use anything to the right because we need more than what the pump's going to give you. So it just will not work. So here is exactly how I want you to do it from the givens, the solution, the equations you're going to use, like handwritten, right? If I go back to here, this is what I want to see on paper or on your tablet, and then say see Excel, and then you can go ahead and do your Excel like we did. Just finish the units in the nomenclature for me, please. Make sure everything is centered, your sig figs are right, and your graph has the correct values. Now this was 45-minute problem that I did, okay, with you. It'll probably take you an hour or an hour and a half to do this, all right? But I hope now this helps you understand pumps, fans, and how to analyze for operating points. If you have questions, concerns, let me know, and best wishes.